Welcome to SysSketch. Think about the last time you logged into a website. You typed your password, hit enter, and got in. Simple. But here's a question most people never think to ask. Does that website actually know your password? The answer is no, and that is not a bug. That is one of the most important design decisions in modern software security. The website you trust with your account has no idea what your password is. It cannot read it. It cannot look it up. And if someone broke in and stole everything, your password would still be hidden. This is the magic of hashing. So what is hashing? At its core, hashing is a one-way transformation. You put a value in, a password, a file, anything, and a hashing algorithm spits out a fixed-length string of letters and numbers. That output is called a hash, or sometimes a digest. The critical word here is one way. You can go from password to hash instantly, but you cannot go from hash back to password, ever. Not without essentially guessing every possible input until you find a match. Let us get concrete about why this matters. In the early days of the web, websites stored passwords exactly as you typed them, plain text. If a hacker broke into the database, every single password was right there to read. This happened, repeatedly. Major services were breached, and millions of raw passwords leaked onto the internet. People reuse passwords across accounts, so one breach cascades into dozens. Engineers needed a way to verify that you knew your password without actually storing your password. Hashing is the answer. Here's an analogy. Imagine a meat grinder. You put a piece of steak in. What comes out is ground meat. You can do this in seconds. But no matter how hard you try, you cannot put that ground meat back together into the original steak. That is hashing. The input gets transformed irreversibly into an output. The grinder is the algorithm. The ground meat is the hash. And the original steak, your password, never needs to be kept around again. Now here's how it works in practice. When you create an account and set a password, the website immediately runs that password through a hashing algorithm. The resulting hash is what gets stored in the database. Your actual password is never saved anywhere. When you log in again, the website takes whatever you typed, hashes it again using the same algorithm, and compares that new hash against the stored one. If they match, you are in. If they do not, access denied. Let us walk through a real example. Say your password is correct horse battery staple, a classic. You register on a site. The system runs that phrase through a hashing function. Out comes a long string, something like 5e8a4 and so on, 64 characters long. That string gets written to the database next to your username. Your real password disappears from memory. When you log in the next day, you type the same phrase. The system hashes it again. The output is identical. The two hashes match. You are authenticated. Now flip this around. Someone breaks into the database and steals the hashes. They see that long 64-character string next to your username. Can they reverse it back to correct horse battery staple? No. The math does not work in that direction. A hash function takes an input of any length, from a single character to an entire novel, and compresses it into a fixed output. Information is lost in that compression, by design. The hash is a fingerprint of the data, not a copy of it. But wait, what stops an attacker from just trying every possible password and seeing which one produces a matching hash? This is a real attack, called a brute force attack, or more specifically when using pre-built tables, a rainbow table attack. It is exactly why the choice of hashing algorithm matters enormously. Early websites used algorithms like MD5 and SHA1. These are fast, dangerously fast. Modern hardware can compute billions of MD5 hashes per second. An attacker with a powerful graphics card can rip through enormous lists of common passwords in minutes. This is why modern password storage uses purpose-built slow hashing algorithms, bcrypt, script, and argon 2. These algorithms are deliberately engineered to be slow and expensive to compute. Not slow for you logging in. That still takes milliseconds. But slow enough that an attacker trying billions of guesses faces months or years of computation instead of minutes. Argon 2, the current gold standard, also uses a large amount of memory during computation. This makes it even harder to parallelize attacks across thousands of chips. Slowness is the feature. There is one more layer that every serious system adds: salting. A salt is a random string generated uniquely for each user and added to their password before hashing. So instead of hashing correct horse battery staple directly, the system hashes correct horse battery staple plus a random 40-character string that was created just for you. The combined value gets hashed, and both the hash and the salt get stored. Why does this matter? Because without salts, two users with the same password produce identical hashes. An attacker could instantly identify all users with the same password, and pre-computed attack tables become viable. With unique salts, even identical passwords produce completely different hashes. Pre-built attack tables become useless. Every password must be attacked individually from scratch. Hashing also goes far beyond passwords. When you download software, the developer publishes a hash of the file. You hash the file you downloaded and compare. If they match, the file is untampered. This is how you verify that software has not been modified in transit. Git, the version control system used by almost every software team on Earth, uses hashing to identify every commit, every file, every change in a codebase. Each commit is literally identified by its hash. Blockchains use hashing to link every block to the one before it. Change one character in any past block and the hash changes, breaking the chain and making tampering immediately visible. You can think of a hash as a unique fingerprint for any piece of data. Two different inputs will almost never produce the same hash. When they do, it is called a collision, and it signals that an algorithm is broken. MD5 and SHA1 are now considered broken for security use, because researchers have demonstrated it is possible to craft collisions. SHA-256 and the SHA-3 family remain secure and are the standard for most non-password cryptographic use today. So the next time you log into a website, here's what is actually happening. Your password travels to the server. The server adds your unique salt. It feeds both through a slow hashing algorithm. It compares the output to what was stored. It throws both away. It tells you yes or no. Your real password never lives on their system, not for a millisecond longer than it takes to hash it. That is hashing, the one-way lock that keeps your password safe even when everything else goes wrong.